Hi everyone, welcome to my talk, Neural Datalog Through Time. Let's start with some thoughts. There are neural embeddings of facts in a large database. Orange dots are special. They represent possible events, and their brightness represent their current probabilities. Suppose you want to model events in some domain where you're an expert. With our little language, you can easily specify a generative model of event sequences, including their timing. Sometimes an event happens that may trigger database updates. According to rules you can write down in our language, it may delete facts, derive new facts. The new facts may derive even newer facts, and also update the neural embeddings and probabilities of other facts. We support a continuous time. That means even between events, as time goes, the embeddings and probabilities can drift. Then what's your job? Your job is to write down some Datalog rules that say what can affect what. It is sort of like writing down dependencies in a graphical model. The rules are logic. They only control which facts are in the database. We use them to define a trainable neural architecture that computes embeddings of the facts, and as we will see, probabilities of the events. In this architecture, the embedding of a fact is a learned function of its provenance, which means all the ways that fact has been derived. So it depends recursively on the embeddings of other facts. You can see that a rule can have capitalized variables. That allows it to pattern match against many facts. So even if you have hundreds of thousands of facts, you may only need to write down a few rules to describe your domain. And a rule uses the same parameters across all the facts it applies to. Now let's see how we use rules to specify a neural architecture. Here is a format of a deductive rule. It is a normal Datalog rule, and it means the new fact is added to the database if these old facts are in the database. Here is an example. When x likes some u and y likes the same u, we deduce that x and y are compatible. We will draw this deduction as a hyperedge. In our neural Datalog, we also have an embedding for each fact in the database. And the embedding of the new fact is computed using the embeddings of old facts. The neural embedding can represent richer information than just whether they like this or not. Now it represents their complex, multidimensional opinions on apples. So let's rename it to opinion. And now they have multidimensional relationship, so we rename it to relation. Now let's see the format of a triggering rule. It is a new kind of rule we add to the Datalog, which means when this event happens, while these are in the database, add this new fact into the database. Here's another kind of triggering rule, which means when this event happens, while these are in the database, delete this old fact. Now let's see how the neural embedding is computed according to deductive rules. Let's use the example of the relationship between Eve and Adam. As I said, it depends on all the ways that fact is derived. Let's start with this way. This rule says their relation depends on their opinions on the same thing. Here's the parameters of this rule. In the database, we have their opinions on apples. So let's compute their contribution to the neural embedding that we want. Remember that variable u can be grounded to more than one thing. For example, Eve and Adam may also have opinions on politics. And these embeddings also contribute to their relationship. Note, when computing the contributions of opinions on different things, the parameters we use are all the same because they are tied to the rule. The parameter sharing makes it possible to generalize to rare and novel events. There may be also rules about how marriage status contribute to the relationship. All these contributions are pulled, plus the LSTM cell of this relation, and then pass through nonlinearity to get embedding of this relationship. The LSTM cell summarizes all the past events that are relevant to this fact. We will show how it works on later slides. Now in the same way, we can compute the relationship between Eve and any other person at Chicago. According to this rule, X is possible to travel to P if X has relationship with someone who is already at P. So we can use these facts together with the facts that they are at Chicago to compute the embedding of Eve travel to Chicago. Now we have contributions of these hyperedges. We pull them at the LSTM cell and pass it through the nonlinearity to get an embedding of Eve travel to Chicago. Good? Wait a minute. Travel is orange, so it is an event. So we still need the probability of its happening. That is just an extra dimension of the embedding. That means we also need to compute an extra dimension for all these contributions by augmenting each parameter matrix with an extra row. Now, let's look at the full picture of computing the neural embedding for a database fact. We compute the contribution of the deductive rules, plus the LSTM cell of this fact, and then pass through nonlinearity to get embedding. The LSTM cell summarizes all the past events that are relevant to this fact according to triggering rules. The overall architecture is a little like stacked LSTM. The deductive rules makes the neural network D at a single time step, while the triggering rules makes it temporally recurrent across time steps. The topology is defined by the deductive rules, the triggering rules, and the events that have happened. Now let's look at the life story of a fact. I mean, how its LSTM cell tracks events. We start with nothing. At some point, an event happens. According to this rule, a fact is added, and its cell is created. The life of this fact continues, and its value drifts with time. Since cell contributes to the embedding computation, the embedding and the probabilities change over time, as in our neural Hawks process. In neural Hawks process, the LSTM cell will be affected by every event, but in our neural Datalog through time, the cell continues to drift until a relevant event happens and triggers a change according to the rule. At some point, a relevant event happens. According to the triggering rule, it will update the cell. The cell may change gradually over time. So when we add or update a cell, we choose a whole trajectory through the embedding space. The embedding will automatically follow that trajectory until another relevant event happens and changes it. Now another event happens. According to this rule, the fact will be deleted and the cell is destroyed. Is this over yet? Well, maybe sometime in the future, the fact will be added again by some other event. Now we know how it works. Let's next see how well it works. We evaluate our method in two domains. The first is where users watch TV programs. This is like a collaborative filtering problem with timing. Who watches what and when? Here are 1,000 users and 49 TV programs to release. There are 49,000 possible watch events, but a program cannot be watched until it is released. Now we release 23, so people can watch it, and more is released, and the database grows. Another domain is where robot soccer teams compete. The database has 22 facts of this form, declaring robot soccer players who play for Team A and Team B. The sequence of events is a soccer game. They may kick the ball, only if they have the ball, or pass the ball, only to a team player, or steal the ball, only from opponent. Such constraints make this database highly dynamic. Okay, now the ball is passed, and the database changes. Our model did pretty well in both domains on several metrics, compared to strong competitors that also leverage both logic and neural networks. If you are interested in more details, please read our paper. We discussed many extensions of the model and more experimental results there. Thanks to the rule structure, we can learn generalization from much less data. Here are learning curves in some synthetic data experiments. At the end, what do we get out of this work? Well, if you want to model temporal data, you can use deep recurrent net. You may or may not know RNN and LSTM, they are good for discrete time case. You may or may not know neural Hawkes process. It is good for continuous time case. Their architecture is basically a hidden state, which you can use to evaluate the probabilities of events. When one of them randomly happens, it will update the hidden state. The hidden state may be large because you have many events to model. In our work, instead of a large hidden state, we have a distributed database of logical facts and their embeddings. The probability of an event may only depend on parts of the database. When an event happens, that would only update parts of the database, and the effect will propagate across parts of the database. The update is derived from a small set of rules, plus their learned low-dimensional parameter matrices. This works well in the domains we have tried, so maybe you want to try our code in your domain? At the end of the talk, I'd like to thank many people and organizations for help with this work, and I also thank the people who come to this talk. I'm especially grateful to Bloomberg for enabling this work through a data science PhD fellowship and an internship in their AI group. Thank you.